Okay, so day 10, I'll do it quick. First, here we have an example. A water plant wants to deliver water to a specific house. So first, it needs to know the address. Second, it needs to set up control line to turn on and off the valve. And third, it needs to set up water pipe so that it can send water to a specific house. So that is the system bus, which is used in the 90s and early 20s. So now the system bus is replaced by point-to-point architecture, which device can communicate directly via packet. So now address and data are encapsulated inside a transaction layer package in PCIe. So this is a pipeline. For example, we have an instruction as add a comma and store it into register S0. The first step or first block is fetching. That means get the instruction here from the memory. And the second step is try to decode the instruction by reading the opcode and also the register here. The third step is execute using the arithmetic logic unit to perform addition operation. And fourth step is to write back to the register. So that is one instruction. We may have multiple instructions and they can line up one by one in a pipeline. So for example, now we have the fifth instruction is waiting. So next step, the fifth instruction gonna push into fetch block here, and then the fourth instruction will go to decode, and it's gonna shift to the right hand side. And after the store process is done, the first instruction is complete. A wafer contains many dies. A die has integrated circuit. To use it, we need to package and add pin, also plastic case to protect it. In order to design, we have three constraints that we need to balance. First is performance, second is power, and the third is area. We always want to reduce the area so that we can pack more transistors to increase the speed. However, if we add more, then the power will increase. So we need to find a balance between them. So microcontroller and microprocessor. The only difference that I know is that microprocessor may require peripheral component, unlike microcontroller that has everything available and ready to use. Next is the process of sending and receiving data involving DMA, direct memory access, I/O block. So this is a high-level explanation. The CPU will send a request to a DMA. Then DMA will follow a interconnect path to get the data from RAM. So now DMA has the data and it can write to the radio, and the radio can send the signal out. So for interconnect topology, there is initiator or requester, target or completer. So they are sharing the same bus. But if there are two initiators, we may need to add an arbitrary block to decide which one has the highest priority. And we can also add a bus bridge to communicate between two buses independently. And next, this is SerDes serializer and this serializer. If we have a node A sending parallel signal, let's say 8-bit here, then the SerDes will using conventional logic to convert or to encode AB 10B. And if you see there's a slash and number 8, that means there are a parallel signal, and the same thing, 10 parallel signal from 10-bit 8-bit 10-bit encoder decoder to serializer, and one line here is just one signal. So after going through the serializer, we just have one signal left. The clock for serializer will be 10 times higher than the clock from node A. And this is a block diagram of the 8-bit 10-bit. It has encoding table, which I think we did in the previous video. And this is a block diagram for the serializer. It takes 10 parallel input and output low voltage differential signal.